Hello, physics students. Glad to be back here solving another problem with you. And this one is problem 15, very similar to problem 14 that I did, and it's going to be quite a bit of stuff on my pad here. I'm trying to do some screen capture, so we'll see how this works. Chemistry's had a few videos. The problems have been less involved than this, and I haven't run out of real estate yet for those, but I've tried to do a lot of things. Feel free to kind of make it save space. Feel free to pause the video and then write some stuff down. And one of the big things is that you need to make sure your picture is good before you start. And I'm sorry, this is pretty not good, so just try to draw my picture out, and actually draw yours and fill your numbers and triple check to make sure you have your numbers. These are all given in the problem here. Ignore these two things for a second, and you're just focusing. This is problem 15, and the focal length of this lens is the 10.7. The focal length of that one is 20 centimeters. You're given this distance here, which they call D2, is 30.2. For me, these are all my numbers. D1 is the distance between these two right here. Okay, and we want to know what is this? Where's the object placed to get this with this system of lenses like this and this image here? Where did this object have to be placed? So we're finding D, this D, which I call D equals question mark. And that's really all that's given in the problem. We got to work backwards. It's basically problem 14 backwards. And as was posted earlier, excellent post by Lincoln, and he said, beware of the signs. And that really is the truth. You got to beware of the signs. It's the formulas we all know, the lens/mirror formula, and then the magnification formula. But we got to work backwards, and other than that, it's basic algebra, and we're done. So we'll go through this, and we'll try to see how it goes. But feel free to pause things. But first stuff, double check this, triple check this. Okay. Well, let's go here. Maybe we'll try a little green. We'll just flop through colors. Happy little green. We could draw a happy little. Oh, come on. No, already screwing up. Brushes. Here we go, happy little tree. We could have a happy little tree, yes. My Bob Ross impersonation. Love Bob Ross. Anyways, back to the problem. So we start with this. This is our final image. Well, okay, so that's DI. So we need DI. Well, which numbers are these? Well, DI is the distance to the optical element. Well, that's this right here. Well, we know from here to here is 52.3, and here to here is 30.2. So the subtraction of those two will get us this initial DI. We can call it DI1 if you wish. So I did that right here. There's a star right there. Ignore the other one for the time being. It's this one right here. Okay, so 20, this is 20. Up here, this green one is 22.1 centimeters in there. Okay, so let's fill into our formula using that. It's 1 over di plus 1 over do equals 1 over f. All right, so 1 over di, we do know that now, 1 over 22.1. But wait, that's an image. If the image is on this left-hand side of the lens, it's going to be a virtual, right? Because the object is going to be, or the image for the first element right here will be here, and then if the second image is right here with it on the same side as the lens, you know that the real light's on the other side, and so this has to be, this is negative. If you check your sign conventions in your packet, you could easily see this. So this actually has a negative sign here. So you got to be mindful of that negative sign. And then we have plus 1 over do equals 1 over 20. All right, when we solve this, I would divide this, get a decimal, divide this, get a decimal, add this over here, and then do 1 divided by this answer, and it will give you DO. That's the simple algebraic steps I would do to solve this. And you end up with 10.498 centimeters. Well, what does that mean? That means that 10.49 centimeters over here, from here to here, is 10.49 centimeters. So our object is here. Well, the object, positive, so it's the same orientation it was. So 10.498 centimeters. This would be our DO. But it's the DO of the first of the second thing. Well, remember, we're working backwards. Will be the DI of this previous one that we've got to do, right? So well, it's not going to be exactly that, but we'll get to that here in a second. Okay, just get that down. We also need magnification. So if we want to do the magnification right now to track it and keep it, it's a negative DI over DO. And so it is, our DI was, it's a negative 22.1 all over, and it's a negative of a negative, right? What is a negative of a negative? That is positive, right? And this gets us a magnification of a positive 2.105, okay? So we don't need that right now. We need that for part 2, but it's better. We'll call this magnification 1 if you wish, and we'll remember that for later. But back to this 10.495, right? All right, well, that distance right there, we need to do the the lens formula for this element right here, okay? So we're going to write that over here. Let's just change colors. It's gray. Oh, let's do gray. And right, so we're doing this lens. Why did not change? There we go. Doing this lens system, or this lens is going to be done in gray. So we'll write this formula down here. 1 over DO plus 1 over DI equals 1 over F, right? But remember, the object for this was the image for this first one, right? But so this is going to be DI, but it's not this number. It is how far it is from this optical element. Well, I'm going to do this in gray right here. This is what I did. Pause if you wish, and you could see that this distance is 52.3 and this is 10.498. 52.3, 10.498. So what is this gray distance? I'm going to draw it in. There. That distance is the distance from the optical element that we're writing this equation for. And when we subtract those two, this is 41.802. I'll just put 8 because I'm running out of room. So remember that. But in this case, it's on the right-hand side of this lens, so it is positive for this equation. It is not negative. So we could put 1 over 41.8. And actually, this DO is our answer here. That's this, which is awesome. And then our focal length is 1 over 10.7. Where did I get that number? Right up here. That's the focal length of this optical element. By the way, these focal lengths are positive because they are converging lenses. Okay, now when we solve, we'll go up here. This is what I do again. Divide this, get those decimals, subtract this over, and then you'll get 1 over DO equals a decimal number or some number here. And then just do 1 divided by that answer, and that flips these, takes these and flips that DO to the top, and then we end up with, checking my math here, 14.381 centimeters. And that should be our answer for part 1. Okay, so that is awesome. A lot going on here. Feel free to pause, make sure you're using your own numbers, make sure you get this whole intricate subtraction, getting the correct distance into your equation too. You hear my children fighting in the background. I need to go referee or be the judge. Actually, I'm I hear all cases and we hold court, and I have to make a decision on the right and the wrong and the repercussions of such things. So you can hear them in the background. I do have the door shut, but oh, never a dull moment. So let's do a magnification number 2, the gray magnification. We'll do this magnification 2. Once again, it's a negative di over do. And what's our di? Our di was so there's my negative sign from there. And it's a negative 40, so it's a positive 41, but it's negative signs in the equation. 41.8. I got it from right here, right? And then DO, which is this solved part here, which is 14.381 centimeters. And when we divide those, we get a negative 2.906. How am I going to make that a 2? There we 2.906, right? Magnifications are unitless. You divide out the same units, it's unitless. So now total magnification, let's get that in. Ooh, we have, well, that's purple. All right. The color of royalty, right? So total magnification is M1 times M2. So now is equal to 2.105 times a negative 2.906, which for me will equal negative 6.117. That is it. So my from the original object to the last image, it will be 6 times greater and will be flipped down. Well, let's look at our picture. There's the original orientation. There's this red one over here is the final orientation here, and it is flipped. So when it was positive over here, it didn't flip the image, it kept it on the same orientation. But this negative sign here meant it was flipped orientation, and that's why we went from down to up here. So we worked our way backwards. That's a very complex problem. The math is not terrible, but it does have a lot of little nuances that you've got to make sure you get right. Go slow, just give it a try, post some, and if I need to revisit it or do some algebra or work through some other things, I can do that. But most common things are sign issues and putting the wrong numbers in the wrong places. So our 2 answers, just to review real quickly, where's my cursor here? Part 1 and part 2 is the magnification. Thank you, and have an incredible day, and I'll see you around. I'm working on making some chess videos and maybe a little push-up contest for some people. But anyways, stay tuned. Be safe.